Good morning. Today's guest is computer science educator and innovator responsible for the design of the Computer and Information Sciences program at Harrisburg University. Professor Majid Shaalan is the program director of this program and has been designing cutting-edge programs for undergraduate students, graduate students, and high school students. As the world turns increasingly to technology to solve its problems, our relationship with the field of computer science keeps evolving. Now, this field started in 1843 when English mathematician Ada Lovelace wrote the first computer algorithm in collaboration with Charles Babbage, who devised the theory of the first programmable computer. But the modern computing machine era really began with Alan Turing's conception of the Turing machine and three Bell Lab scientists' invention of the transistor, which made modern science and modern computing possible. Now, the first computer science degree actually was in the early 1950s, 1960s, and the first distinct academic discipline and degree was offered by the University of Cambridge Computer Lab in 1953. In the US, the first computer science degree program was offered by Purdue University in 1962. Now, since the 60s, like many things, the field has evolved rapidly. And Majid is here today to share his insight on how he sees the field evolve. Majid, welcome to the Future of Technology, and we're looking forward to hearing you tell us a little bit more about Harrisburg University's programs and the field of computer science education. Over to you now.
Hey, thank you,
Majid?
Sure. Thank you, Preetha. Thank you for the nice introduction. It's not going to be easy to talk about what is happening in computer science and how it evolves and where we're heading in a very short, meeting like that, or something that you can put on few slides. So, but I tried my best and I put something that I can share with everybody. So a little bit about us and about the university, Harrisburg University of Science Technology, and our very young program. This is a screenshot from an article that you can find here probably and see all the details about it. We ended up being the second best online program for the master's degree, and that was really very encouraging news, because that was right after our master program kicked off late fall 16. So that was after probably 6 or 7 months, which is a great news for us, but it's also a big responsibility. So I want to go from there and start, probably saying something about myself as the guy who, architectured this thing. But of course, there is a big team at the university. It's not only me. This is not a one-man job, but, if they wanted to blame somebody if something going wrong, then it's going to be me. I would accept that. So here we go. So this is where this story started. This is my bachelor degree. It was in mathematics. It's in this very old university. It's actually, this is the newest version that is built on, after the original madrasa, we call it in Arabic. That was in Baghdad in 1227. And that's the picture. You can read more about this and the biggest library ever at that time, and all the historical developments about it, who taught there, how it is related to algebra, how it is related to House of Wisdom at the time, and so on. So one of the things that made me think to put this on the slideshow is that although no matter what is happening there now, the era where I grew up in Baghdad, you can feel the sense of the importance of science and math. Like when we were kids, was kind of, unless you're a mathematician or a poet, or an artist, you would be a loser. So we picked up the pace from that young age and move on. So I ended up being in the mathematics department. I didn't like it first, but it turned to be just like my destiny. So I moved then after the revolution of computers and everything is computerized, and I thought this would be a good way to express all mathematical concepts and how much they can change the world through this great new tool that is coming around. So I got my master's degree, University Baghdad, another university, more recent university than Al Mustansriya, and I got the PhD also as well there. Uh, so then, moved to the United States around 2006, and here is some of the experience in academia that I, went through. I'm currently the professor and director of the Computer Information Science program. Now, recently, I've been assigned to the graduate school and the master's and the PhD program that is hopefully coming soon. Before that, I spent about 8 years in the state of Colorado, teaching in the main three schools in different, assignments. And before that, Al Mansur University College, where I spent about 7 years as a computer science professor. And before that, University Baghdad, that's where I started as a lab, TA, where I absorbed all of these, wonderful things and picked up my own, style in programming and, problem analysis and so on. So some of the experience in the academia, that's where after I got my bachelor, you have to serve in the military there. And I, did some stuff with the military. Then after that, I was an application programmer in a manufacturing committee, the main one in Iraq. Then moved up scale to be a researcher with the Central Committee of Research and Development. Then some consultant, positions here and there. Then that's where I moved to the United States. I started with the project VERB with the ARPA. That was through University of Colorado Boulder, and then did some natural language processing with the Boulder Language Technologies. It was very short time, but it was a great experience to get to know. It was the dream that computer scientists from all over the world would think that America would be the right place for them. That's where computers and IT world is thriving. So it was a good experience till I, spent 8 years there teaching and doing stuff. Then I got picked up by Harrisburg University of Science Technology, and that's where, that was very interesting moment in my life. Where I got the opportunity to express what I believe, to express my vision to computer science with full support from the leadership here. So we started to work together, looking at the community, looking at the industry, chatting with the leaders around here to craft going our own computer science program. All of these variables are making this process not an easy one, but it has been fun for me. So I'm gonna, take it from what Preetha mentioned about Ada and Babbage and go all the way to Turing and all what is happening currently, where millions of people can contribute, compute way faster than you know these big names, and where every citizen can have a share to contribute to the science movement and to computer science and technology. We probably want to mention a few things about the state of computing currently, what is happening with us here, and there is nothing that one can, summarize this journey better than Moore's law and how it shaped up the everything happening around us. Moore's law. This is about how many transistors you place on a square inch on a chip, and it is probably again one of the most interesting things that is can trace down and up all the improvements and achievements in the computer science and information technology. So in between very simple machines, analytical machines, all the way to whatever NVIDIA cards that are doing with their GPUs and stuff like that. Quite exciting journey. One of the very important moments in the history of computer science and information technology is 2007. And I have to admit that, I'm very impressed by what Thomas Friedman put in his book, Thank You for Being Late. He summarized all of these things and in a way showed that 2007 was a defining moment in our life. It is only because what happened in 2008, the meltdown of the real estate market and stuff like that, took all of the joy and happiness of all of these achievements in 2007. Some of these things that, as you have remember, first time that smartphone Steve Jobs pulled and talked about a tiny device that has an operating system connected to the internet, a touch screen, no buttons, no other things, which is changed the world, and I think forever, especially if you are keeping up with the upgrading your Apple smartphone. So that was one of the achievements at the time. Then that was just like a starting point, not really for the others, but in parallel things were going. Facebook and Zuckerberg and what happened on all levels, and then Twitter and Hadoop and big data, where now we have an operating system that is running all of these small systems around the world, and having all of these piles, huge centers of data that is collecting data and information about almost everything. Then we got into, back to Moore's law, and we got into how much the cost of generating 1 megabyte of data and how much does it cost to transmit it, where started, probably another revolution of people sharing everything, the open source software concepts, GitHub, Google, YouTube, which is one of the stuff that we're doing now, Amazon, Kindle, IBM Watson, two drop off guys thought about hotel reservation and how they can get some money out of it. They started renting their places, and we got Airbnb, and so on and so on. And that year, the users on internet hit the billion user at the time, which is a great deal. Then we started to get all of these, following up in all different, fields of science. The sequence of human genome and the price with the new applications, the big drop in price, and how it was, started a new generation of, research about the genomes and other things. Solar powers also kicked off in 2007, and so on. So you probably can put this in, and this is actually from the same resource of Thomas Friedman. You can see the cost of the generating 1 mega of data and transmitting it. And you can see that there is the intersection is around 2007, 2008 here. Should be a little bit to the left, I think. But that's defining moment where things are dropped, big drop in creating data and big rise in ability to transmitting data. And that's the power of what we have now, what is so-called cloud, which is I really liked how Thomas Friedman like commented on the name cloud. He finds the word cloud is very soft, and he called it supernova, and he has all, he got it right, because this is something that is changing the world. Look at these 300 cloud computing companies from around the world, and you don't want to talk about the war among them, and their ability to dominate the computing power in the world, and in a way that is very lovely, because when you say they dominate the computing power, it seems kind of bad thing, but they are also, because they are adopting the open source initiative, they are reaching out to everybody that can have access to the cloud, and give them people the ability to contribute and share and learn. So that's the software as a service. Applications, I don't think this illustration is enough to tell or to show the applications that are going around. If you want to, research this, you can probably run into a lot of bigger list and better visualization, but you can feel it even without this, that we are surrounded in this ocean of applications that is touching everything that we do throughout the day. It is start to be very fast to catch up with, and honestly, I can tell and share this with you, for a person who is tasked to mentor a program, and looking at my students and the market, and how to fill the gap in between, how to get somebody very well equipped to take on all of these challenges. It's one of the biggest tasks that I have ever been assigned, and I have been through a lot, like quite a bit, but that's a different story. Probably I'm going to write a novel someday about it. But to this point, this is how it is too fast. Like it's about and I think people from cognitive science would probably better talk about it than me, but you can tell that human adaptability to technology is really very challenging, and we cannot just keep up with things. Although no matter where you're at on that spectrum of computer science, it is challenging. We in computer science always say that, we're on top of it because we can write codes and we're programmers. Okay, here's the news. Google, how many programming languages are there? Last year it was 300 something. This year now it's 400 something. Every new thing has its own programming language or domain specific language, and so on and so on. It's all moving toward making it very easy for people not only to use applications, but also to have their own access control to applications by designing domain specific languages. Very simple example, and as I grew up as a database programmer, I at some point I thought that there is nothing in the world like other than database programming. Then I discovered that the software that we use, which actually the API that we have used at the time, was written in C. So I did, there is something called C. Okay, let's see what it is. And you move on, and you see that for every field in life, or every activity, we have things that is automating everything and having people be able to So in my point now, I'm talking about SQL or SQL languages, which is, for database programmers is like the ultimate tool, but it is a domain specific language that enable people who are dealing with data to do their stuff in a very easier way, and achieve all of these things, while people who are probably doing data management in C++ are really unable to pull that much of achievements or ability to manipulate data. So again, for everything now we have a language. We have a class in our graduate level, which is theory computation, that I teach with some other faculty. Uh, uh, the projects there is about developing a domain-specific language. We have a class in the undergraduate, which is theory of automata, that I had 3 students here in Harrisburg University. One of them designed his own domain-specific language that early, which is very, interesting if you want to look at it from any point of view. So, what is happening because of that? We are facing real world scenarios everywhere. It's kind of, if you live enough, you would find it kind of, I don't know, funny, or it's interesting when everybody's talking about computerizing systems and big data and predictions and data science. A few months ago, I had a invitation, one of many, to visit an insurance company. And I was just like, oh, let's see what those guys are going to tell me. Then it was very surprisingly, the IT department and the designers and the system analysts and the data cubes and the analytics stuff to enhance, improve their, business theory. So, and that's just one example. But wherever you go, there are real world problems that need help from computer scientists, which is going to take us to our side on how we can help, how we can teach our students to be the new generation of helpers. So if you look at the challenge, is that huge amount of data to be analyzed around, whether it's business, whether it's finance, whether it's a research center, whether it's a scientific computing, and so you're always faced by huge amount of data to analyze, numerous number of variables, because you do not analyze just to analyze, you analyze to model. The model is to find a formula. Formula is composed of variables. So when you get into this level, you would be like really very impressed by how things are getting complicated. There is a YouTube clip for a mathematician, scientist in energy field. She showed some of their experiments. There is 50 million variables and hundreds of thousands of equations, of like differential equations for the behavior of a system. And you can tell what you need to model, optimize, analyze, predict on such a system, and how big burden is this. And there is a lot of things that is coming with the real world scenarios that are surrounding us that probably needs hours and hours to describe. But let's use this to move on toward how we comprehended all of this and used it to develop some vision or theory in the education world. And again, this is not easy. Education is one of the very slow pace, difficult area to make change. People in academia probably would feel and know that. People who are now in the industry run at some point from academia was because of that. People who want to go back to academia now need to hear that. It is a very difficult take, but if you are just like lucky as I feel now, and you get a hub like Harrisburg University and given the opportunity to innovate you would probably make sense of what we're going to say now. So these are some of the examples that I probably should have clicked on this earlier. Different examples from what is going on around the world of how data is playing a role and how complex systems are going on. So we have a tremendously high-dimensional, multi-tiered hypotheses around the world that we need to capture, analyze, model, probably predict, and help make decisions. So that's the whole world of a computer, like if you want to call it a secret life of a computer scientist. Comprehend these high dimensional hypotheses and try make sense of them and do what they can do to show decision makers simple visualization to help them make decisions. And these decisions are huge decisions. So now, how this thing is becoming possible. It shouldn't be that possible. If you, again, lived enough as a programmer or somebody who is big fan of writing codes, we used to hide our codes from each other. We used to emphasize living in a bubble, and we would refer to this as, oh, this is being kind of, wow, this is your thing. You shouldn't be, let it go because this represents you, and so on, so on, so. Thankfully, the world is changing. Things that is about sharing are proved to be very helpful to enhance and improve, programmers themselves, styles, and create a new world of that. So we're going to talk a little bit about it. So we're going to start probably with where this started first, in democratization, the science itself. And there are a few examples one can probably use. Here is a saying from Michael Nelson in his book, Reinventing Discovery. Multiple minds would be more powerful than one, for sure. That they would stimulate each other with different expertise and perspectives and collectively make easy work of hard mathematical problems. A few examples that we can use. Here are some of the characteristics that feature this initiative or movement. There was this thing started with polymath project at some point. One of the mathematicians, posted on his blog a problem, complicated problem in mathematics, and asked people to contribute to, and things started with few comments, and then some very well-known mathematicians jumped into the discussion, and so on, so on, so in 7 or 8 months that blog was thriving with all kind of stuff that is really interesting. And by the end of that problem is solved, and people started to talk about different level of problems, and that showed how brainstorming and sharing really helpful to solve problems. Another experiment is the gene bank, when the scientists not only collaborated, but they invented things on how to deal with the knowledge they have. And if you want to read about that project, it's a very fascinating information that you can find. Then the relationships in between science and society. Galaxy Zoo, one of the projects, one of the scientists posted a picture from a telescope, and that you didn't know, what is this? So posted there, I think it was a female scientist, or a female citizen, just a regular person, picked up that and ran with it, and then they discovered a new planets in the galaxy. And that project is now one of the big hubs around the world for astronomers and other people interested in that field. uh, all of these three projects, and you can probably find tens and if not hundreds of these projects. I should have probably put the GitHub here as a representative for what is happening in computer science. I think would be in this slide, should be. So this thing is not, we didn't invent it, but because we own the tool, we're supposed to be the masters of the cloud computing, and all of these blogs and stuff probably have a good leverage to do our stuff. So here's a saying, I think this is from Qualcomm Research Center, that is saying, lives are changed when people connect. Life is changed when everything is connected. And here you go, you have this great platform where people can exchange knowledge, learn from each other, no matter what you hear, no matter what we know about some, bad way to use these things, influencing people's political opinions and stuff like that. Still, this world is fascinating. Uh, uh, so that's what I'm saying here. All computerized tools, and I'm trying to narrow down this, conversation toward, what we do as computer scientists. Uh, uh, so if you look at these problems and you probably try to make sense of these and want to see what you need to move on, what you need to, equip your students with so they can survive this very accelerating world of knowledge, you would say, okay, you need a high performance computing capability. Uh, I'm again feel very lucky to be part of building an HPC machine for this university from scratch. We have been given the opportunity to rent or to use a cloud computing ability with Amazon or with Google, with anybody else. We did that, but we also just so we be, on top of, the details of building the machine and have our students have the experience to hands-on experience to build the machine. We built a machine here, and we have a group of students. We're going to be, like in November, going to Dallas, Texas for a supercomputing conference, taking 7 of our students to get hands-on there, and some of the faculty, in an attempt just to accommodate the situation, because it is, you just can't wait for this. You don't know what's going to happen tomorrow, and you just like wake up, you find yourself outdated, you own all your tools. So the challenge is also, and we're getting now deeper and deeper, better mathematical modeling techniques. By the end of the day, this thing is started to be shaped by, intelligence itself, whether it's our human intelligence or it's a machine intelligence. The more we can model of real-world problem and find some formulas and then generalize them ourselves, the more we'll be able to help machines to do that and then automate things. So this thing moves into, from human intelligence to artificial intelligence to intelligent automation. Everything now is supposed to be automated because we are able to have some advanced mathematical techniques. Examples, tensors and tensor flows, which is, if you dig deep in that, you will see a very neat way to model a very complex, multi-tiered, hierarchical hypothesis using tensors, and you would appreciate a product like TensorFlow from Google that can help realize this ability. We still need for, and again, this thing wouldn't be possible unless it started with a richer the hunt for a richer class of data representation, and dig deep in mathematics to pull tensors and then build tensor flows based on that. We're still looking for more efficient, iterative, recursive algorithms, and this is the challenge every time. You can probably tell how much this relates to new disruptive technologies like blockchain, where blocks are composed of multi-layer hashing functions using Merkle trees, which is a data structure, and then all the way to build the chain through communication protocols that is also based on that hashing. So this is the deepest knowledge probably of these technologies that a computer scientist is supposed to be very well prepared for. So we still need to be more open, get out of the bubble, brainstorm, and learn from the others. Computer science is a science. Science and scientists are the best observers on the planet. We have to communicate, look, analyze, see where we can help and apply the knowledge that we have. Adopt more modern computing tools. In computer science, there is a phenomena that I stick with the programming language that I have learned and I have achieved, and I have done all of this. Example, myself, I have done all of this all the way, to get my PhD. I was a Pascal programming, then a C programmer, but when I had the opportunity here to build the program, it is not the case that I want to impose what I think is good for me, because it's not about me. It's about the new generation and what is the best, tool. And I'm not saying that Python is the best tool, but we found out that this is the easiest, so we can transfer all our knowledge and experience to our students, hook them up to the great community that is mentoring Python and other tools, that is all the API stacks, all the Keras, Pandas, TensorFlow again, Theo, and other tools. That is, if computer scientists are not going to pay attention to this, they need to pay attention to the fact that a data scientist person can produce probably 10 papers in 2, 4, 3 years, while a computer scientist cannot pull one paper in that time, because they are using these very advanced, helpful tools, and not really relying on one programming language to do everything. If you want to do anything Alexa is doing using, C++, how big this task would be, while if you see the pile of APIs that people are using, working on such neat projects, you will feel that it is really changing the narrative and changing the world of computer science. So from my perspective, one apple a day keeps the doctor away. The way I see this in computer science is actually, once upon a day, an apple hit a guy. That guy thought about how to find the mathematical justification for that apple that is falling from the tree, and he got the breakthrough in physics about gravity and other stuff, Newton. And in between this guy and another guy who got hit by another apple, or I don't know, he just took a bite of that apple and create some neat systems around. And the way we understood this is that it's in between physical sciences and computer science. There is a hidden loop that not everybody is aware about. When physical sciences are in their quest doing analysis to the phenomena to find out how to describe it using laws of mathematics. And we have all these achievements now. From computer science point of view, we are looking at how to, use the mathematical formulas to model systems that we are not sure that they are correct, but we want to prove that it is correct. So we create some artificial phenomena and we simulate it. And this is the whole quest of computer science. And then when we prove it, it would go back to the physical sciences. A very interesting part of my journey was in artificial intelligence when things are going around. So this cycle can go the other way, by the way. If you want to verify your findings, you go back to the real world and world of physics and see how far you are from reality. We have a physics scientist here that I really enjoy talking to, but that's a different story. But the thing that I said about AI, I'm in the area of artificial neural networks. So when we got into from laws of math and we created an artificial brain and we called it artificial neural networks, and we started achieving things and proving things and learning the machine through things, we thought that, okay, if this is successful with machine, then this must be the way our brain is working. So we started from a biological model and we created artificial model. Then now we are meeting cognitive scientists on how learning is happening in a human brain. And this cycle is going in different directions and really enriching the scientific discussion in between, these parties and helping each other to prove their things. So on this side, cognitive science are collecting observations on patients and developing theories. We actually take these from math and do things and then create our theories about learning. And if these two pieces are, connected, the world would, and this is what is happening, the world is, really witnessing a great achievement. I also have a scientist here who is from cognitive science that I always talk to and run things by him, and he's doing the same thing with me, and it is very interesting when you open to people and discuss things. So and all of this is because of this guy who connected these two worlds. This is Alan Turing and his theories and his achievements. If you want to dig a little bit behind the name, you're going to find this guy. Interesting things about him, 4 huge achievements in his life. And probably the most interesting thing is that there are some people saying that this guy is the guy who stopped the Second World War. Read about the Enigma project and read about the new boats that used to sail, very close to New Jersey, and the exchange of all of that knowledge between the United States and Britain at the time, and why the D-Day was there and why we jumped into the war and all of that stuff. So read about it. So we took all of this momentum and tried to interpret this in a little program experiment. So we got into, here is what we have, a very diverse, place where things are in between theory and applications, engineers, scientists, programmers, developers, hardware, software, and you have to figure out your way out of this mess. You don't want to, bias to one side, because this way you're going to label all your graduates with this label, which is unfair. And you cannot deny somebody, because you have to be open to everybody and make everybody feel that they have a share in you as an educator. So you can see that this is signature definition for computer science. I'm not, claiming that I discovered this, but I am very well known that this is my thing. So to reflect on all what we have said, here is how we think that computer science should, be, so we can also see where we're going from here. What people are seeing is just like the tip of the iceberg, all applications. The very huge part of computation is hidden from people, and that's our world. In between the applications and the machine, there is a long journey that a programmer or a student needs to know to produce such applications. From the machine to the representation, to the modeling, to the algorithmic thinking, and to the ability to write codes, then produce applications. And we are very aware about this, and the whole program is actually built around these things. So in another way, we define computer science. These are programs of springs of algorithms exploited by constraints, exposed by representations that enable computations. And computation for us is two types of computation: a smart one and a non-smart one. The conventional systems, which is for every programmer, this is the fundamental knowledge. You have an equation that has variables, you define variables, whatever programming language you use, and you verify the results, get the results to verify that equation working. That's very fundamental thing. This is Fortran style, formula translation. This is the basic one. It's not less important than the AI, but this is the fundamental one that is everybody should go through. And this is doing a lot of stuff around our world. The other part, so there is no learning capability to the machine. A programmer is the master. You have to do everything. With any change, you have to go back and redesign. The other part is when machines do not need a programmer to update their internal behavior to accommodate systems and adapt itself to the surrounding, which can be labeled differently depending on the application. It could be called generally intelligent systems. It could be data mining system, or you analyze data, extract a pattern, generalize that pattern, and make predictions. It could be robotics, where you can understand reasoning and learn from the environment and actuate and do things in a very kind of little visualization. Here is an environment. It's supposed to be a child anyway. This is supposed to be not a child, and the system's supposed to be able to have a computational component inside it, and sensor, sense, percept, and then decide what to do, and then actuate and take action. And it's a very nice marriage in between science, computer science, math, and mechanical engineering, and Internet of Things and such and such. But it is all based on a non-conventional computational system. So for us, and as an educator, we go through, we have to kind of map this all the way to go down how courses are built in our program. So we have the first part, how to understand problems and how to analyze them. You apply Polya, legendary Polya 4 steps. That is very well known to everybody, to analyze and develop a plan. Then you need to know how to represent things. You have two things in this world of computer science: the data itself and the computation, which is supposed to be based on a logical, basis. So if you go with the route of data, you move to discrete structures, and that's where discrete mathematics is a big deal in computer science, Harrisburg University. And then you move on to data structures, and then you move on to coding, and then you move on to developing solutions. And this part is, science, art, magic, a lot of stuff. Geeks would understand this thing differently, other people. When it comes to the computation, You have the logic, you have the Turing machine, the automata theory, how to automate things, finite state machines. Then the algorithms that are built on top of that. And these two are enabling coding, or let's say the best practice of coding. You know, coding and programming is a big deal. Somebody can just like learn it. We call it, you know, for fun, we call it monkey style. You can just like mimic others and develop things, or you can do it as a scientist when you understand your data structures and algorithms and what is behind the scene. This way you can pull a solution that probably never existed before, and that's the difference in between a computer scientist and a software developer. Some computer scientist is somebody who's tasked to find the solution for a problem probably never been solved before. It's unknown. A developer would go with what that guy produced of a software and develop things and build on top. They are both of them very important, but we need to differentiate in between these two things. This is why we have two different concentrations in computer science and software engineering. So the more you know about these, the more you're going to be able to produce things. And, you know, a testimony for that, I'm not sure how much it's, you know, useful to use an article, how this article, you know, came about. I have no idea, but we have been recognized that we're having some good program. What are the measures? I have no idea, but at least we have been recognized. And there is a lot that is going on here. Didn't like make it to the public so far. So again, to this trip, we believe computer science is science. It's about the main fundamental questions and scenarios that can be generated from an experiment. We believe that computer science is just a simulator for everything that is supported by theoretical computer science, numerical methods, computer vision, numerical analysis. We believe and this is what is actually the graduate program is built around. It's a computational science program. You know, part of it is the, you know, the ambition that we feel that we want to do something different. And also, so it's, you know, kind of analysis that, you know, you don't want to run against Google and Amazon and Microsoft, develop new programming languages or create a new operating system or whatever. You want to apply the knowledge you have to serve, you know, humanity and all different fields of science. And that's where computational science is sitting. This will be probably our PhD program that hopefully coming soon. So we think that science is based on three pillars: theory and all what math has brought to science; experiment, that's where physics interpreted math; and we think that the third leg is simulation. And probably this slide is more you know, clear to explain that. So real world systems into, you know, experiments, into, you know, results, and then the cycle, and then findings, and that's physics. The other side of the world is modeling through mathematics. I know this animation is not working like specifically as it should be, but at this point you have the two giants, mathematics and physics, and all the scientific methods are attached to these two till you have the computer science. It's not that we didn't have simulators before, but computer science changed the world. If you don't believe, ask, you know, Boeing when they have the first simulator, and a pilot would, when fail, wouldn't burn a $30 million airplane. It's just like, you know, just like a message on a screen that you're dead. That's it. So this is the cost for training. It's when computer science got into this to simulate things, and actually you run it by the two old giants through, you know, validation, to validate your findings or simulator findings with physics and experiments, and verification by running this against the mathematical laws and the mathematical verification and proofs. So this is another illustration. It is the hierarchy: problem solving, analysis, mathematical modeling, numerical methods, and numerical simulation. And this would probably help us get into the scientific finding, and these are the the pillars of that. Another way, there is always a cycle of redesign to go back and forth, enhance in every stage of that. Best way to learn programming, and that is very kind of a biased area, because coming from somebody who teaches programming, like, what do we think that our students or people who are into learning programming, it's a very big initiative. There we have presidents who called to learn coding, and we have everybody. Harrisburg University is very fortunate to have the opportunity to reach out to the community around here, middle schools, high schools, and we're sending messengers to teach people programming, because we know this will change their lives. Especially, we are located in an underserved area, so this is really means a lot to everybody. So what is the best advice to be given to people? I tried to put some of the stuff here. So the method of learning styles. Some people would say students can learn by visual, effects. Some others by different, ways, voice, and other things. There is not one style that is very successful and dominating, and the research is telling that people can learn from different ways by different methods. So we are trying to come up with a combination of everything. Even with the personal inside the program, we have an instructor in the classroom, we have a TA, we have somebody who helps with office hours, and we, like, as an example, we feel that students could learn from another students who is a TA probably better than a faculty with a tie and a suit and probably mustache. There is probably burden of learning. So we play all of these things around. Being part of a community to learn a lot. You don't need me to tell you a story about Stack Overflow or GitHub. It's a different world now. People are open to share their ideas. People are more willing to help. So reach out, be part of one of these communities. So they give you, a lift, and they will help you to improve yourself and your style. Just don't stay in the bubble. Be responsive to the change. Brainstorm. Disrupt. Don't be passive. Learn from people who are using live coding, not slideshows just like mine. As a head of program here, programming language faculty are vetted by me, and I always say, okay, we need a lecture on data structures, and you need to use a split screen slides, and there is a code, live code, because this will let. This is not only about this specific thing and having the instructor to be embarrassed. No, it's a different perspective. When you use live coding, you will make mistakes. Your code is not going to run from the first attempt. So this is a very learning moment that, hey, students, you can make mistakes, but you have to go back and fix things and brainstorm about it. Take a step back and look at your code. This is how people will learn. You learn from your mistakes more than anything else. Again, this is probably something I already said. Be part of the learning process, and not just like settle down and just listen and not trying things on your own. I encourage students here to challenge their faculty, because this will help us get the best from each other. Use pair programming. This is what is happening. Two students on one computer. One of them is the driver. The other one is doing, the one is coding. The other one is checking for syntax and stuff. And they switch things around. This is going to help a lot. A stronger programmer can help a weaker programmer. This is going to help develop a programming style. Till you get your own programming style, which is not an easy journey, these things can be very helpful. Worked examples. If you're part of these communities, say GitHub, you can go see all kinds of examples. You can run them. You can learn from them. This is not a problem. You don't have to be ashamed about this. You learn from things. This is how everybody is learning. People are reading books to learn things, to say things next day in a better way. Why a programmer should be ashamed looking to other codes? This is very natural. But at some point, you need to be able to pull a solution. At some point, you need to be hired and pull and be a standalone programmer. But this is how you can help yourself move on. The more you know, the more you run examples, the more you're going to be able to write better codes. Very practical advice. Focus on one language, because it's not about the syntax of the language. You should learn the logic of programming. The language would be, another thing. All languages have the same thing, a burger is a burger. You can say it in Arabic, in English, in France. People will understand you. The way it is done, the way it's prepared is the same, although people talk in different languages. So at some point, if you are a beginner, you choose a language that is easy to pick up, and I would highly recommend Python. And then you can move on with whatever the challenge are going to take you. But do not distract yourself with multiple programming languages, because when it comes to syntax and practicing in a live session, every programming language has its own. So do not distract yourself with these things. Probably for later, keep it. What else? Do not just code, because it's not only about coding. As we have said, it's about computation and whatever big concepts behind the scene going on. So try always to dig deep behind these keywords that you use in your programming language. So that's all what I was able to think of. It is not easy to be in this position to go over a very interesting topic and then give people advice. But this is what we do every day. This is how we go about computer science, and how to help our students being better day after day after day. The school has a very interesting things, although we are a very small school. But as a program head, one of my problems is to accommodate senior students, because our students are getting full-time job offers in their third year. And there are statistics behind these. Probably confidentiality wouldn't let us share it with you, but this is a fact. Because we are doing it the way that you have seen. So that was a good opportunity to talk about it. And back to you, Preetha, if you have more questions for me or whatever, I'll be more than happy to answer. Thank you.
Thank you. Thank you so much, Majid. It was very, very useful to hear all of this stuff and really see the whole context of where computer science as a field is going, these new ideas of democratizing computer science education and how millions of users are now collaborating together. And I think it gives us all a really good sense of the kinds of programs we offer here at Harrisburg University. So I do appreciate your time this morning, and to everybody else, please reach out to me if you have questions on this or want to learn more. Majid and I work very closely on these initiatives. So once again, thank you very much all for listening, and thank you, Majid, for spending time today with us.
Thank you so much.